When you talk about urban vegetation, you usually would expect perhaps something like that, like plants growing at buildings, between buildings, and so on. But today's talk is more on less prominent growth. And well, it depends on your view, if you find it nice or not nice. I will come to that later on. And there is a question, why do you look on these things, on microorganisms and cryptogams growing on the surface of buildings? And well, in Germany, some years ago, there was recorded a dramatic increase of surface growth on facades. And there were discussed several potential causes. So, you know of the acid rain, sulfur dioxide pollution was reduced, and this sulfur dioxide was poisonous to algae and mold fungi that might want to grow on the surface. So when this was reduced, there was more potential that they could colonize. On the other hand, I call it increasing eutrophication of the atmosphere, because we got much more nitrogen compounds, there are hydrocarbons, there are other pollution matters that increased in the same time. We have also the global environmental change, which changed the climate, and some places it may have more precipitation, but we had also a change in the surface moisture due to increased thermal insulation, and I will try to explain a little bit, because if you have a traditional monolithic wall, the plaster is directly on the built-up wall, on the wall build, and on the warmth from the room behind, part of it may go through. But if you have a modern building, you often have the external thermal insulation compound system, and here you have the insulator, and there is the thin plaster layers on top of it, and this prevents that warmth goes through. And this may lead during the night that the stored heat beams off and the surface gets a lower temperature than the air itself. So here you see a graph of measurements. You have the dew point temperature, that's the temperature when the moisture begins to precipitate, when water condensates. And usually the traditional monolithic wall stays above it, but the insulated wall with the very thin layer then may go below it, and that will mean that it will get moistened, that it will be wet. And this, of course, is a source of growth. We did a lot of investigations, and we also had a lot of specimens exposed at different places in Germany, and we wanted to record the early microbial colonization during, let's say, 5 years, and we were focused on the visible growth. What we find is an interesting picture, because in literature you often find the expression biofilm on buildings, but our same pictures didn't show any bacteria, because what you see here is a microcolony of a fungus, and there are no rods of bacteria there. And here another picture, also fungi colonizing a masonry, and again there are no bacteria clearly visible. So this, what we have on the building surface, is not a biofilm by definition. It is a so-called biocrust. It consists of algae, fungi, and other things. We had a really close look on it, and we tried to identify, if possible, down the species level. It was not always possible, and you can see from the forms that emerged. We had a a great variety of living things that emerged, that colonized the surfaces. So we have the blue-green algae, we have some bacteria, but not really clearly forming a biofilm. We have even red algae. We have then different algae related to the brown algae. We have the green algae, of course, and the red sign is for the forms that had the greatest diversity. And, of course, where there is plant life, you usually also have animals, and I will come to that a little bit later. So, what's the species count? You must imagine this is during the first 5 years of a built-up wall of masonry, and we have some blue-greens, but the huge variety is in the green algae and also in the Ascomycetes. And you can see from my graph, when I started, the imperfect fungi, they were still as a group represented, but now taxonomy has found out that most of them belong to Ascomycetes, so now they are together here. I built up a collection of building relevant microorganisms. We now hold many cultures, but these represent about 300 to 400 strains. And we also made a new discovery, Fraunhofer alga. We named it Excentrochloris fraunhoferiana because it was found on the area of the Fraunhofer Institute. But I will come to it again. So now I will show you a little bit of this diversity of the aspects, because with the naked eye you usually can't see these things. And so we made biocultures and some photographs. And you will realize that I may have a little bit a different pronunciation of the Latin names than you usually would have, so I apologize for that. You see here Porphyridium purpureum. This is one of the very rare forms of the red algae that is living on land and may even colonize building surfaces. It has a very special ecology because it really loves nitrogen, it loves salt, and therefore it usually is only on special locations where we have this combination. So it's in former days, when the hygiene was not so high, it was often found around pubs and so on. And here we have Haematococcus pluvialis. I will also come later back to it again. Same with the Gleocapsa sanguinea. It's a blue-green algae that may colonize the surfaces, and this is a special group of algae. It's from the Eustigmatophyceae. It's usually a soil algae, and some of them are a major part of the plankton, of the marine plankton. So this is the red and orange aspect, but most of it usually is green. And this is a kind of a bigger unicellular algae, and it has more nuclei in their cells. Here is another thing that makes this little small elongated cells. Here we have Elliptochloris reniformis. This may have two kinds of spores, rod-shaped and spherical ones. And here's another Xanthophyceae, it's a Chlorelidium astigmatum. So there is a huge range of unicellular algae you find there which have not so many differences. Then, of course, we have the filamentous algae. We have some of them which make packets, like Apatococcus lobatus. Then we have the undivided filaments, like Clepsomedium flaccidum, or divided filaments. Then the Polia aurea usually forms a really nice orange patch, and here's Brasiolopsis ramosa, which is a very compact alga. And if it's on the surface of a building, it usually looks very similar to that alga. But I just mentioned many of them look quite similar, and then we have also some critical forms. In this case, you may call it the alga, formerly known as chlorella, because many of them now have been assigned to other genera and have been further divided. So formerly Chlorella saccharophila, now is called Chloroidium. Same with Chlorella angusta-ellipsoidea. When we did our investigations of the surfaces, Chlorella tribuxyrides still was a special form, but now it's merged with this alga. And then there is former Chlorella luteoviridis. I think the genus is now Xanthochlorella. There are other critical forms, complex forms, like the genus Stichococcus, who usually forms like the type alga, Stichococcus bacillaris, small, really very small rods. And now taxonomists have found out that all the others belong to different genera. Here now, during the investigations, we found a form that we could not identify from the literature, and so we found out it's not described yet. So we described this new alga. This has quite huge cells, has many chloroplasts, and has really a very odd form here, like a fungus, like a puffball. And we dared to name it after Fraunhofer, the namesake for the Fraunhofer Society. But also other colleagues, they isolated different forms, I think I also found on my surfaces. And this here is Celastrella aeroterrestrica, and it's typical. It also formerly was in a group that was called Chlorella, but now it's in a different group of algae. And you see these very fine ridges on the surface of the cells, which are very characteristic. You can't see them with the light microscope, but you can see them then in SEM pictures. And this is one of the diagnostic features of this alga. But of course, it's not only algae that might grow on modern building surfaces. It's also a lot of different, you might call them mold fungi. And one of the complex forms is the genus Cladosporium. And in the literature I had for differentiation, I found these forms, but now each of them represents a whole group of closely related species. But in the first instance, they seem rather similar. What's typical for these forms, you can see it here. They have a dark color because most fungi, mold fungi, are sensitive to irradiation, and some of them who are growing in an irradiated situation produce these dark pigments. It's melanin, the same compound we have in our skin, and this protects them for against the light. And as I showed such pictures to our customers, they said, "What? Now the fungi and the algae are united and against us." So we find also lichens there. But we know it's a special symbiosis between certain fungi and certain algae. But some of the algae I showed you before are capable of forming a symbiosis with special fungi. And these aspects here, they are about the size of a millimeter, because you can see here the kernel of the plaster. This is 2 to 3 millimeters, and here's the beginning thallus of the alga. It's interesting because they have these odd structures with them. They adhere at the surface, and they are really fastened very well. And in the beginning, as you see, they are rather tiny, but of course, later on, they may become more conspicuous. The yellow form you saw before is Xanthoria bariotina. It's one of the lichens that is unusually resistant to pollution, so you still find it in the cities. Also some Fistia species can stand higher pollution than other lichens, and this then may reach the size of several centimeters in diameter. Now a very special topic is the early colonization of building surfaces by bryophytes, especially often you find specimens of the genus Schistidium, and I got kind of interested in this kind of moss because it's also a critical genus, but of course there are also some other mosses. This is just a potpourri. There are a few others that are emerging rather early. It might be Hypnum sopressiformi, Tortula muralis, Bryum argentium is also, because it's also quite pollution resistant, and there are a few others like Grimias and Eucalypta or Tortella. But still I was fascinated on Schistidium, and I'm very proud I got 3 synthesis grants where I could investigate them more closely. This would not have been possible at my institute. Apart from the forms I showed you previously, also some animal life forms may occur, as for instance here, this very small amoeba, perhaps a Valcampia, and also Rotatoria like this species. This is the habit when it's active, but when it's drying out, all of this goes in here and then it looks like a very little orange egg. And of course, also on the building surfaces, vascular plants would try to colonize, but in difference to the other forms I showed, they need some space for their roots that they can live there, and therefore this depends then a little bit more on the structure of the surfaces. And very typically in Germany I found Asplenium trichomanes and also Cymbalarium borealis, which are really on very exposed spaces perhaps. So, and perhaps you recognized these forms we find on masonry. They all have their special stories. So for instance, Hematococcus pluvialis, it's a green alga, but it has a high amount of a red pigment. It's a kind of a carotenoid called astaxanthin. And this astaxanthin, this compound, is also used when they breed salmon, that it gets this nice orange color. Then they feed the fishes also astaxanthin. But it may be produced, it is produced with this alga, but for the industrial scale, I think it is produced different. And this alga has a special kind of ecology because it's specialized on periodically drying up water bodies. And so you may find it on a windowsill, but you may also find it on some structures on the building, on the masonry. And it can stand the periodic desiccation because as soon as it's wet again here, they will start again to produce and to multiply. Another alga, Trendipolia iulitus, it has a, if you rub on it, it has a scent of violets, but it's kind of odd because some of us can smell violets and some of us cannot. So it always depends when I make my trick. if the person I'm dealing with can smell violet odor. But the alga itself is specialized on mineral surfaces, so it likes to have calcium in its substrate, like here on this concrete wall. And under the microscope, it's much more beautiful than here on the wall. Another feature of this alga here, of Glircapsa sanguinea, which is a blue-green alga, it has usually a reddish color in its slime sheath of the cells, but this is also a pH indicator because it changes its color at pH 6.5, and this is the original probe from a surface. So at this border, the pH should be 6.5, and here it should be higher, and here it's lower. Then these organisms, some of them are good friends and like each other, and some of them are not. So this is with this formerly called Ulocladium hudemansi, now Alternaria botrytis, which forms this really beautiful spores. It likes to eat other fungi, so it's antagonistic to other fungi. But unfortunately, we won't like to use it on masonry because, as you see, it has a very bad dark color. So if it eats up all the other fungi, then the surface might get black, and we don't like that usually. Then you can find special organs of these cryptogams or microorganisms. Like here, for instance, from a green surface, it was all covered in these brood cells from a moss. So it didn't develop to further stages, but obviously these brood cells could multiply by themselves. And here another example, it's Orthotrichum anomalum, and this has a permanent protonema, which sometimes may be the only stage of this moss you find on the surface. Then it might look like an alga, like Trentipolia. And here you see there is a little bud, which then grows to the normal plant, and usually would have a habitus like that. Okay. Yes. So if we talk about the succession, we realized that in the very beginning, often mildews and mold fungi dominate the surface. And this is because in these plaster formulations, we often have some organic compounds. And if you have the established surface, some animals, birds, and insects may set on it or nearby, and they might leave some presents which are very good for fungi. And I will show a picture of this a little bit later. And afterwards, if it's moist enough, then the algae may occur, and they usually a little bit longer to achieve a visibility, that you see the green dots or yellow or orange dots. And of course, the normal process of soiling is starting on these surfaces, like on every rock and soil and so on. But the bacteria we haven't seen as prominent. And I must admit, we have looked only on the aerobic bacteria and counted them as a whole and not further differentiated. But we did not see, as I said, a real biofilm on the surface. And after a few years, usually, there may develop some lichens or bryophytes, and we see a gradual shift also in algae and fungi to species that like to stay there for a longer time. So from the ecological view, so-called stayers. And depending on the structure of the surface, if there is room for some roots, then also vascular plants may colonize even after a few years. And this is a feature we have especially in our climate here in Central Europe. This is corresponding to the seasons. Also, this growth on the surface is kind of cyclic because during the hot months, when it's dry, there is a stagnation or even a regress, and then in the autumn it starts again, and also during winter it comes to a kind of a little stop, and so, but usually it don't vanishes complete, but just starts on a higher level the next year. And we also saw that the nutrient input on the surface is an important factor for the establishment of microorganisms, because this here has been a bird dropping, which later fell off, but you still see the fungi are quite happy. And again, it's fungi with a dark color, and this may be a problem for the surface, for the owner, because especially in Germany, if they have bought a white surface, they expect that it stays clean and white forever, and then these things might not be accepted. Well, and to the overall conditions, so you must imagine that a surface like a masonry, a building surface, is kind of an extreme environment. We have huge changes in moisture, we have considerable changes in temperature, and all these things, and we might also have extreme pHs. So from all the organisms we recorded, we took these values together, and so we can say at least a relative humidity of 68% is necessary that these things can grow. So there are a few algae and a few mold fungi that can start their growth at this value. The temperature is just depends on what organism you have. The minus 15 degrees are, I think, from an alga that also lives in the Antarctic. And there are also some fungi like penicillium which can go below zero, and they can do that because they have so-called compatible solutes in their cell sap, or they have some other compounds that are diluted, and so they can stay active below 0 degrees. And then there are some, especially fungi, which can stand rather high temperatures, and these figures are counted for the vegetative phase, because if these organisms have the time to change to a dormant stage, they will stand even higher or lower temperatures. And so there are some of these algae we found that can stand very low pH, but usually on a plaster you have a tendency to higher pHs, and so I found above 11, pH 11, there is not the danger that something will grow. This is for every organism too high. But below, and there are also these fungi that can produce some acids, so we could expect growth if the other conditions are okay. Of course, algae need irradiation, but not only the algae. In some mold fungi, it's essential that they have irradiation during the day, that they can form their spores. And then there are needed some traces of nutrients. For the algae, it's enough if they have inorganic nutrients, but fungi, they need organic compounds. The impact of these things on the surface is still discussed controversially. It's a discussion of biodeterioration, versus bioprotection, because we see some organisms occurring on the facades may damage materials, they may produce acids, they may be active in kind of a physical way that they swell and shrink and thus produce strain on the surface. But there are also other organisms that may harden the surface, because if they are building up a layer of oxalate, this is very hard and may protect the surface for physical strain. And on one hand, surface growth may intensify the moisture load, because if they swell, if they take up water, there is more water on the surface for some time. But we have also forms, like I've shown you, Apatococcus lobatus, who repel water, because their surface is water repellent. So in this respect, there are more investigations necessary to clarify the relations on the facades. Now I come to management of surface growth on masonry, and there is a deal of physical measures you can take, but usually they aim to reduce the water, the moisture on the surface. So you can have greater roof projection, you can enhance the surface hydrophoby, also with a technique called superhydrophoby is included the so-called lotus effect. You can make the surface smoother so that the water runs off, and you can use pigmented surfaces because they take up more irradiation and transform it to heat, so the surface will dry more easily. It's the same with the infrared coatings, because they reflect the warmth back into the layer. And there is also phase change materials, because when
just 5 minutes.
Fine. And if they change their phase, if they condensate, they will give up, will release some warmth. And so you can do some physical measures to reduce water on surfaces. An alternative are chemical techniques. Usually they are used biocide combinations. You have biocides against fungi and biocides against algae. And the problem is these solutions are often limited in duration, because the biocide will be washed out sometime. You can also have cleaning procedures, for instance, using pressurized water beams, or even there is a technique with carbon dioxide ice. But be careful with this, because I've read an article that in Scotland, all the lichens of the church towers were removed by water beam, and a year or so later it was green because of algae, because the algae were released, and yes, we're happy about it. So, and I must admit, biological measures for use on building surfaces are still underdeveloped. So what we saw is sometimes there are special fungi, in this case from the genus Erysiphales, which eat up mosses and algae on the surface. But in this case, I think it does not look nice at all. Then it's a picture here from Edinburgh. There are some snails which are eager to eat algae and things from the surface. Perhaps we could use them to clean our surfaces, I don't know. And now we come to the opposite. Would it be helpful if we enhance the growth on the surfaces? And then we must realize in a natural situation, here on a concrete wall, here in a specimen of plaster, this is usually a development that looks patchy and inhomogeneous, and most people don't like it. So the acceptance is low. If we could achieve nicer colors, like here on a wall in Switzerland, I think, and a more homogeneous growth, then perhaps the acceptance would be much better. And also these small things, they have some impact on the ecosystem services. So we made some trials with this. This is also produced a few years ago, 2017, here in the Royal Botanic Garden of Edinburgh, when I tried to fix mosses on lightweight concrete. So I made the surface a little bit more rough, and I put on a special mixture to, you can say, to glue it on the surface, which also contains some nutrients. But this wasn't really stable because I left some of the specimens here, and the water washed away, but after more than 5 years, there is still some green on it. I had more success with aerated concrete, but yesterday I learned here there are some problems with aerated concrete, and although the mosses are growing happily on the surface, there are two issues. One issue is the scale up, because if you want to green a wall like the size here, you want to be finished after a few hours. You don't want to have to work on it for a longer time. And the other thing is aerated concrete. The form I used is not stable in the environment because it can't stand ice formation. It will crack. So another trial I made is I have isolated all these interesting algae which can stand all these harsh conditions. I tried to put them on deliberately, and so far this is the result. You can put algae on these surfaces, but I think it can still be improved. So now I'm finished. What I wanted to show you is a different aspect of urban vegetation, and I wanted to show you that there is much more biodiversity on surfaces of building than you would expect, and you even now you could find new species. And what is decisive on the surfaces is microclimate, but microclimate is even too big because we are talking here on a scale of millimeters and centimeters. So the nanoclimate on the surfaces is decisive, especially in form of water availability for this growth. And you have different options for management to get rid of them or to enhance them. And I'm convinced if we find a proper way to establish the nice algae and mosses on the surface, it would offer new perspectives in the ecological design of buildings and the urban environment. And here, for the end, there are also some inhabitants of masonry. Thank you.